In this section, 19.4, we're going to talk about the efficiency of heat engines. And remember, when we're talking about a heat engine here, we're not just talking about a train in the 1800s. We're talking about all of the means of producing energy from either nuclear power or from fossil fuels. And this encompasses, of course, a central role in our study of energy, support of our society, and our issues of environmental issues of global warming and other issues that are really critical for our planet and for our society. So how efficient can these systems be, and what is involved? Well, first of all, what heat engines do is they take in heat and they output work. And the efficiency is the work that we get out divided by the heat that we put in. Well, now remember, if we look at the heat that we put in, it's going to be the work plus, this is the heat that's in the system, is the work plus the heat that leaves the system in the form of cold. If we look at the efficiency is going to be work divided by, it's going to be by definition, efficiency is the work divided by Q hot. Remember, if we think about this engine, the best way to think of it is we have a hot reservoir. And this hot reservoir has energy that flows to work, and it also has some that flows down here to a cold reservoir. So this is right here the energy, the heat that flows out of the hot place, like the boiler. This is the work that flows this way, and this is the heat that flows to the cold place. Now, it is ideal that we would take all of the energy and make it into work. That can't be done according to the second law of thermodynamics. There's no way that we can take heat and make it all into useful work. That's because a great deal of this heat is in the form of random motion. And so it's just not possible for us to convert it all to work. Some of it will still be in a random form like this. In fact, entropy for this process must stay zero or must increase. Now, the efficiency is therefore how much work we have here that we're able to get from the heat that flows or leaves this hot place. So now having this, what we can do is we can say, oh, let's take the work and write it as Q hot minus Q cold. That's because the difference, this energy conservation by the first law of thermodynamics, this energy here plus this energy must equal to this, which we've written up here. So we can write it this way and divide by Q hot. And what that results in is 1 minus Q cold over Q hot. So how do we make this efficiency great? We make the efficiency really great by having this go down to a really, really cold place, near absolute zero if we could, but we can't do that, of course, here on Earth easily. And we want this to be a really hot place. Ideally, this would be the sun and this would be outer space, which is almost at absolute zero. So that would be the ultimate type of engine giving us the most efficiency that we could possibly have, because then this would be near zero and this would be a huge number, and therefore our efficiency would be near 1, which is near 100%. Okay, remember all those quantities are positive. Now, I need to tell you about a Carnot engine. A Carnot engine is an engine that operates in a reversible manner, and we'll discuss that Carnot engine more later. But the Carnot engine goes through a series of cycles in its process of isothermals and adiabatics that allows it to be reversible, and it is the most efficient engine that is conceivably possible. This was proved in the 1800s, that no efficiency could be greater than that of a Carnot engine. And Carnot was able to show that this term, Q cold over Q hot, for a Carnot cycle was T cold over T hot. Now this is very important because this says the ultimate efficiency, therefore, for an engine is to use a very cold source. Remember, this is at a temperature hot, this is at a temperature cold, that this ratio will obtain. Therefore, we can write the efficiency, the maximum efficiency we could possibly have, the maximum efficiency for a Carnot engine, it's for a Carnot engine, and it's going to be 1 minus, and now we replace this term as T cold over T hot. This is an incredibly important equation because this says in order to have really high efficiency, we must have, and of course these temperatures are in Kelvin as they always are in thermodynamics. This must be a very high temperature and this must be a very low temperature. So now we know what kind of efficiency could be obtained. Now this does not cover things like friction. You're only going to have frictional losses, you're going to have transmission losses, you'll have storage losses and so forth. This is just to get the work out of the system. Now let's look for the theoretical best efficiency we could get for our power plants. In a power plant, we might have, say, 750 Kelvin for our hot temperature and 300 Kelvin for our cold. 300 Kelvin? Why is that? Well, it turns out that 300 Kelvin, 300 degrees Kelvin, is generally taken to be the temperature of the surface of the Earth. Remember, outer space is about 3 degrees, 2.7 degrees Kelvin. But if we're going to do this process on Earth, then we've got to get that heat to go somewhere. And where's it going to go? It's going to go into a river or the air or somewhere else. And on the average, remember we have 273.15. And so what this is it's about 27 degrees above our zero or melting ice. And that's about 27 degrees Celsius. And that's generally accepted as a nice round number for the expected temperature that we're going to discharge our heat into. Remember, at your power plant, you've got to cool one end of this thing. The heat has to come out, this exhaust. And the best way you can do it is to run at one end of your turbine. If you think of your turbine here, I guess I could draw a propeller better than that. And this is going to be hot gas going this way. This is going to be, it's going to turn this turbine, it's going to expand. And as the gas expands, it's going to be cooler. But if we could put coils here to really cool this down and get this gas really cold, remember this is steam, we want to condense it out, then we create a big vacuum here. And we can do that by running water through this that comes from a river. And so we can cool one end, and the other end is as hot as can be, the other end is cold as can be, but that coldest end can only be about 300 degrees. You say, okay, I'll accept the fact that the rivers and the air and so forth on Earth are about 300 degrees, 27 degrees above freezing Celsius. But can't we get this hot temperature to be much hotter? Well, our temperature of 750 is about the best we can do, because above that we get much more expensive engineering problems. We begin to melt the steel. We begin to have valves and everything that don't operate properly. And so this becomes an extremely high temperature. And this is effective for both coal and for nuclear power. It doesn't matter what you're burning. This is about as hot as you can make the boiler. And you make this fluid, usually water, at 750 degrees Kelvin, the steam, and you're going to cool it down to about 300. And so this is the best efficiency you can have. So you can quickly calculate what this efficiency is, and you'll find it's about 60%. In other words, 0.6. Now, that's considered the standard temperature on Earth. So if we work this out, we get about 0.6 or 60%. But actually, if we look in real life, the temperature, this is theoretical in theory. But if we look at epsilon max in real life, we find that these other losses take another 40%, so that we're down to about 40%, so that our actual efficiency is about 40%, or 0.4. So we're losing 20% loss to friction and other causes. Loss to friction and other causes, transmission losses and so forth like that, or even in addition to that. Well, this is how much electricity we're going to get out of this system. Now, what does this tell us? This is one of the sources of the greatest problems that we have today with our global warming. If we are going to use either nuclear or any fuel, if we're going to use heat as a source of energy, then we're only going to get 40% of it in useful work. Well, where does the other 60% go? The other 60% goes into the environment, either to the coal reservoir or out here to the environment in the form of friction, in operating the turbines and everything else. So 60, you might say, 40% ends up as useful work, 60% goes out into the environment, so 60% is heat to the environment. That is the air, the river, and so forth in the environment. Well, if you think of all of the electric power that's produced on Earth, then this is a tremendous amount of loss that we have. And this is going to be the same for something like an automobile. Roughly speaking, is that you're going to lose at least 60%. In fact, it's not even that efficient because we can achieve this by using a huge boiler at very high temperatures, and that's with the absolute maximum efficiency and cooling the system at the other end using river water. And you'll notice that these plants, the coal-fired plants and the nuclear plants, are always built near a river or some large source of water that can perform this cooling. So this is kind of disturbing if you stop and think about it. Every time we make 100 calories, 60 of those go into the environment and 40 of those get used. So that presents a real problem. Now, the next thing I want to talk about are how efficient are our appliances and things of that nature, and the kind of heat pumps that we have. So 19.4 Part B, I want to discuss some of these other issues. These are the terminology for this, for refrigerators and for heat pumps, is called the coefficient of performance. And you remember that basically what happens with a refrigerator or a heat pump is basically the same. What I have is I have coils over here, and I have coils over here, and I have a pump. The pump runs on electricity. So I turn the electricity on, the thermostat will turn it on, and what it does is it begins to compress the fluid, and this compressed fluid here begins to expand. As the fluid expands, then of course when anything that's compressed expands, then of course it becomes cold. So here's the compressed fluid moving around here. These coils become very cold. Then as this fluid, like Freon or some other coolant, moves around here, then what we want to do is it becomes hot. So we want to blow air over it. That's a little turbine there. We blow air over it to cool it off and compress it again. So we get hot out this end, because after it's expanded it becomes hot, and then we compress it and it becomes cold. And as it goes around this cycle, of course we're using electricity to create cold and hot places. Well, we could imagine that this cold place, and now I'm going to draw it this way, cold, this is inside a refrigerator. And out here is the hot, and this is the room. So obviously opening the refrigerator door is not going to do very much to trying to fix the heat in the room, because the more the thing runs, it's not at 100%. The cold is not going to balance the heat that's coming out underneath. So anyway, this is the way our refrigerator runs. Now, it's the same way that an air conditioner runs. So this could be considered an air conditioner also. So what we do is we pass a fan over this, run the cold air out into the room, but we want to take this hot part then, and this is then called a heat pump because it's pumping heat from one place to another. We put this outside. And we put these coils inside. And as the fan blows over these coils where this the coolant is rapidly expanding, these coils are extremely cold, and of course that cools the air in the room. And then over here, we take it outside and we get rid of that heat that it took on inside, and take that heat outside, blow a fan over it, blow the heat outside, and everything is nice because we get the air conditioned inside. Now, what we can do is we can turn this around in the winter and do the exact opposite. We can take this part and exhaust it to the outside and let this fan blow into the inside of the house. This is winter. This is summer. This is winter. And so now the heat from these coils is coming inside your house and heating your house. And what you're really trying to do is you're trying to air condition the outdoors. So these cold coils are actually picking up heat from the outside. You can say, well, is this process really working? Well, actually it is, because these cold coils will pick up some heat, even in the winter, from the outside. Although the colder it gets out here, the less efficient this system is. It turns out that in a state like South Carolina, this system is more efficient by about a factor of 2. So it has an efficiency of 200% over just taking the electricity, the electricity that we're putting into the system, taking that electricity and just using a straight heater to heat. So you're much better off doing this than having a heater. If you go to a cheap store and you buy an area heater, it's going to cost you twice as much to heat in South Carolina than it would cost here. But when you go up into the north, though, and you get really cold up in Michigan, this heat pump is not going to be very efficient because it's so cold outside, it's almost as cold as this, so you're not pumping much heat in the reverse direction. Therefore, the heat pump is not effective there, and you have to use gas or some other means to heat the house. And even in South Carolina, in many places, if natural gas is available, it's more cost effective to use natural gas than it is to use a reversed heat pump. Of course, natural gas isn't available everywhere, so you have to use that. The coefficient of performance for a refrigerator is the cold heat divided by the work. And of course, we want less and less of this amount of heat that goes into the cold reservoir, and we want a greater and greater amount of work. And this ratio is called the coefficient of performance. If I look at a heat pump, the coefficient of performance of a heat pump is equal to the heat that I have that comes out divided by the work I have. Because what I want to do there is I'm interested in how much heat I can produce for a given amount of work. And remember, I said that efficiency was about 200% in South Carolina for a heat pump. You can use these numbers now to relate them back to what is called the energy efficiency ratio, as advertised on appliances and so forth, or often they will have the coefficient of performance there.